Welcome. Today we're going to learn the basics of linear programming, a math method used to find best outcome under certain limits or constraints. Whether it's maximizing profit or minimizing cost, linear programming helps us make smart decisions. It uses inequalities, graphs, and a goal to optimize. Basically, linear programming is a way to find the best solution to a problem where there are limits or constraints. We can use it to minimize cost, maximize profit, stay within time, budget, or space limits. It uses inequalities to show the limits, a graph to show all possible answers, a goal to decide the best choice, like I've said before. Here's a real life example. We are running a snack stand and we sell burgers for $5 profit each and tacos for $8 profit each. Here's the constraints. Only 60 minutes to cook, and we want to make the most profit. This is a linear programming problem. Let's talk about modeling constraints with inequalities. A constraint is a limit, something you can't go over. In linear programming, we use inequalities to describe those limits. Here's a real-world example. Burgers take 10 minutes to cook. Tacos take 5 minutes to cook. We only have 60 minutes. Let's define our variables. X, the number of burgers. Y, the number of tacos. Let's write an inequality. We know each burger takes 10 minutes to cook, and each taco takes 5 minutes. So 10x plus 5y is less than or equal to 60, because we cannot go over 60 minutes. We also add other constraints. We can't cook a negative number of items, so x greater than or equal to 0 and y greater than or equal to 0. Here's what we just did. We turned a real problem into math, and we wrote an inequality that models our time limit. So we're setting boundaries for our variables. No negative numbers of items for food. Let's move on to graphing feasible regions. A feasible region shows all the possible solutions that work with our constraints. The part of the graph where all the inequalities overlap. Any point inside this region is a valid solution. Let's continue with the snack stand example. We set this inequality up for time. And we also have x greater than or equal to 0 and y greater than or equal to 0 because we cannot have a negative number of food items. Let's rewrite this main inequality as an equation to make a boundary line. 10x plus 5y equal to 60. Now we have to find the x and y intercepts. For x equal to 0, the y would be 12. So our x-intercept would be 0, 12. Or the y-intercept would be 0, 12, sorry. And if y is 0, x is 6. So the x-intercept is 6, 0. So we draw a line from 0, 12 to 6, 0. Y-intercept to x-intercept. Now we shade a region below the line because it's less than or equal to. And we can only include the first quadrant because there are no negative burgers or tacos. So here's our feasible region right here. So now we have to identify vertices of feasible regions. So from the above graph, the feasible region is a triangle, as we can see. So the x-intercept, 6, 0, as we talked about before. The y-intercept is 0, 12. And the origin is also another vertice. 0, 0, 0, 12, and 6, 0. X-intercept, y-intercept, origin. These are our vertices. So, how do we optimize this quantity? We are trying to find the most profit. So, we do this by checking all the vertices. So, we're trying to find the best value that would give us the most money. So, we're selling burgers for $5 profit each and tacos for $8 profit each. So our profit function is f of x, 5x plus 8y. and we want to maximize this. As we talked about before, the vertices are the origin, the 6, 0, and 0, 12, the x-intercept and the y-intercept. So we plug in these vertices into the profit function. And here we see that for the y-intercept, our profit is maximized. We get a max value of $96. So we should sell 0 burgers and 12 tacos to make a maximum profit of 96, as long as this is allowed by our time and resources. So in linear programming, maximum or minimum value of the function will always happen at one of the corner points, called vertices of the feasible region. This works because the function we're optimizing is a straight line. The highest or lowest point it touches will always be an edge. So here's a quick little bit visualization. How far can we move this profit line so that it still touches the blue area? So, using systems of inequalities in context. So a system is where we have more than one inequality. So they all have to be true at the same time. This happens when we have multiple limits. Here, we only had one main limit. And here, so we have to stay within all of these limits. So here's a real world example. We run a small bakery. We make chocolate cookies, which take 2 minutes to bake, oatmeal cookies, 1 minute to bake. We only have 8 minutes each day to bake cookies. Kind of far-fetched, but let's say we're very busy. So we can only make 6 cookies total per day because our tray is small. We earn $3 for each chocolate cookie, $2 for each oatmeal cookie. What is the most money we can make in a day? So here, we're optimizing. So let's define the variables. X is the chocolate cookies. Y is the number of oatmeal cookies. The time limit is 2x plus y is less than or equal to 8, because it takes 2 minutes per chocolate cookie and 1 minute per oatmeal cookie. And our tray limit is 6 because we can only carry that many. So x plus y less than or equal to 6. And we cannot have negative cookies. So x greater than or equal to 0 and y greater than or equal to 0. So we have to write the maximum profit function. So that's 3x plus 2y, and we want to maximize this. So we're finding the corner points of this feasible region. So we find the intercepts for 2x plus y equal to 8 first. So that's 0, 8 and 4, 0. And then the intercepts for x plus y equal to 6, which is 0, 6 and 6, 0. And we find the intersection of the two lines by setting them equal. So they intersect at 2, 4. So now we run through all of these, the set of corner points, to check if they're valid. 0, 8 and 6, 0 do not work because one fails the tray limit and one fails the time limit. So our valid set of corner points is just 4, 0, 0, 6, 2, 4, 0, 0. And yeah, here's the feasible region graph. So we have this shaded area here, and we see our corner points clearly. These two do not work, so we only have 4. So yeah, let me get rid of this one real quick. So now we plug it into the profit function. 0, 0 gives us 0 profit. 4, 0 gives us $12. 0, 6 gives us $12. But 2, 4, the part where these two lines intersect, gives us 6 plus 8, which is 14. Our maximum profit is $14, which is achieved by baking 2 chocolate and 4 oatmeal cookies. And that's it. So this is the magic of linear programming. We define variables, write inequalities, graph the feasible region, identify vertices, and plug into our goal function. The solution is always at a corner. Thank you for listening. Hope you tune in next time.